if you want, I can go ahead and get started. It's actually the timing is really interesting because we're quite literally analyzing the 45 color experiment that we just ran. So we're right on the cusp of that. I don't have anything to share that's specific for that, but I can tell you that it went well, and it's very. I'm using this as a transition in, but it's really interesting because what we're doing now is looking at how you can iteratively do panel design and take away traditional labels and then replace them essentially one at a time with NovaFluors. So we're seeing some really interesting stuff. Like we dropped out BB515, CF568, and now PE-Sci5 and one other marker out of a panel. You can actually quite literally watch spread being removed out of a panel, and you can go back in and see when you replace marginal spread being added. And so it's really, really interesting because we're kind of in this, it almost feels like a wave, right? Because you have this sort of like the wave that's going through the panel where you're adding in floors, but then you're adding essentially marginal spread back in for these markers across the panel. So it's really, really interesting. But some of the things we will talk about that is new is the ability for us to actually print antibodies. And it's actually that capability that enabled us to do the 45 colors. So I will mention that in this talk. And we can do that now both for in-stock antibodies and also for anything that's shipped to us. So validated that we can actually do it at 1-to-1. So I will mention that here. So it's pretty exciting to be like, oh my gosh, it worked. And we got up to 45. Now, of course, I've got a huge problem for the rest of the week, which is analyzing the data. But yeah, so maybe as an introduction, talk about conventional dyes, talk about our technology, talk about where we're taking it. That make sense?
Oh, great.
Let's do it. So what is conventional dye performance? And we won't dwell on the technology. I think we all know that. But I think what's important here is what is conventional dye performance, right? And the answer is, well, with PE and PE dazzle, you get, I think which we're all familiar with, you get cross excitation, right? Which has had huge impact even on the way our instruments are designed, right? Think about the Fortessa having such a few number of detectors off of the blue. It is entirely because of this, right? And it's because of this cross excitation we get with PE dazzle, which of course then manifests itself in spillover spreading, and then also just an inability to leverage blue detectors on any instrument, right? So we're actually just getting some data now from LSR2, same problem. Cytoflex, same problem, right? I mean, this is pernicious across the field. And the other type that we see, other type of fluorophore behavior that we see is something that might be narrowly excited, but very broadly emissive, right? And BB510, which is one of our favorite violet dyes to pick on, but it represents a lot of the polymer dyes, honestly, is this notion that you get this very, very broad emission peak as well. And so, I think one of the things that we've always looked at subjectively, and then we'll also look at objectively, and it's the way we've been thinking around all of our panel design efforts in leveraging more fluorophores and thinking around this dynamic of what do traditional dyes do and what could you leverage with a NovaFluor, and then what could be possible there in leveraging all the detectors on an instrument is, in an ideal world, yeah, by definition, the compensated data would have the medians lined up. But in addition to that, actually the standard deviation would also be equivalent, right? And for what it's worth, I mean, this would enable us to do much more on automated analysis. It would make biological interpretation of the data much, much easier. And that's the thing that I still get excited about, because if you can have clean fluorescence infrastructure, then you can enable a lot off of the analysis piece. Instead, what we get is measurement error, right? Which is spillover spreading, right? Due to photon counting. But regardless, right, that photon counting error increases with not only with signal intensity, but also just the fact that we have these fluorophores that perform in a certain way. The way we've been thinking about this is both the perpetrator, which is APC, and then PE-Sci7, which in this case is a canonical victim. But if you think about it, you can also total up all of the ways and all of the different fluorophores that this perpetrator is spilling into, and then you can look at it. And in fact, what we've been doing, the reason that we're able to build the panels I was mentioning earlier, is we quite literally go out and set a hit list for fluors, right? And the way that we set those hit lists is we look at the sum of spectral spread that's being added from one fluorophore into the detection of all other fluors. And we say that's one that needs to be removed if we want to go in either direction, either deeper into immunophenotyping, right? Because we're working with folks who are looking at 20, 25, 28 colors on a per phenotype basis, right? So if we go very, very deep down the tree, or if we're going to do more of a survey course, right, and go to 45, and we've got other people who are working up to 52 colors, right? That's what's going to enable us to do this, is go in there and take out those dyes that are spreading quite substantially. And so I'll describe some of the stuff we've been doing here, but we quite literally set up a ranking of like, okay, these are the worst performing labels. How do we take them out and replace? And so, the other context here, of course, is that dyes have always driven hardware development, right? And in fact, for what it's worth, also democratization, because you get development in the high end, then you get much better benchtop instruments, for instance, or benchtop sorters. This occurred with the PE tandems, which led to the response of the 12 color VAX Vantage, quantum dots leading to the response of the 18 color LSR2. And it continues today, right? I mean, we've got the development of the Brilliant dyes and the development of VAX Symphony in response, right? And then, similarly, and I think hopefully this frames it well, and at least what we've seen is, at least based on the older fluorescence infrastructure, really spectral is a response to a question, which is how do you get so much more out of having such a limited set of dyes, right? Which have fundamental constraints, not only in terms of where they can be excited to emit, but also in terms of their performance characteristics, at least to date, right? And this is based on non-ideal dye performance. Non-ideal dye performance actually has a name, right? We call them signatures now, but it is non-ideal, right? And there is no magic wand that's provided to us by spectral to remove the spreading here. Photon counting is photon counting, right? Even though you can increase the theoretical number of colors per panel. But one of the plots that I generated somewhat jokingly, and then it became a thing, was like, what would a perfect label be, right? And actually, it's been a lot of customer conversations that have led me to show that there's actually some other interesting pieces of this. Not only would you have a label that emits perfectly and hits one detector, but you would also be able to tune the brightness of that label so that you would essentially normalize your biology across different antigen densities, right? So that you could actually manage intensity, right? Which I think is a really interesting concept. So you could go both low or high. So that's something that we've done on 2 of our blue dyes, and now we're actually building out quite a bit more dynamic range, particularly as of this past week. So we've got some new results where you can do several, possibly even orders of magnitude of dynamic range, right? And so go much, much lower. But then, of course, similarly on the other end of it, if you got something like CD44 or 45, tune that down so that signal intensity also doesn't lead to spread in the panel. Then if we titrate down from that perfection, if you will, we have a tad less than perfect blue, and then we have some emission into the blue, but that's really it, right? And I think that's really kind of where, honestly, probably where most of our labels are hitting, right? And association data from a customer in a moment, that is actually what his plot looks like is kind of a lot like a tad less than perfect blue, right? So the way we've thought about this is, well, what if you could start over? What if you could design a fluorescent label from scratch? And so I'll show the platform technology, and then I'll show you some of the things that we've done, and then how we followed that on with now 17 unique colors, 19 labels, because within those colors, we've got 2 that actually you can choose the brightness, right? And actually those are ones that we're getting out CD4 kits and conjugation kits out for within the next couple of weeks. So I think the first thing that we would say is every label needs to be bright and clean, should be silent on the violet. Consistency and stability, this is something we've done a lot, particularly recent work on, in addition to showing some intracellular results as well. All that's brand new, as well as some of the longer term consistency and stability testing we've done. And then controllable brightness in terms of the way that it actually is working is something that we're doing now. I'll also say that on the controllable brightness piece, I'll give an update there as well, which isn't in the slides, which is one of the questions we've had also is if you have 2 different brightnesses, could you actually use those to phenotype different markers and put them all in the same channel? And so we're right on the cusp of figuring out, okay, is that possible? And could you actually separate the 2 out, right, and do CD4 on one, CD8 on the other, and then have the bevy of other markers that you have? So I'm hopeful that we're actually going to have an answer on that in the next 2 days, which I think would be pretty exciting as you think about stacking up different channels. So how do we do any of this? We take small organic dyes and bind them onto these oligonucleotides, and then we can assemble them, actually self-assemble into this phyton structure. And this phyton structure has this cruciform shape, and it actually has these crossover regions, and that's actually what provides its stability, right? And actually, I always like to bring something new because Catherine and I do a lot of these. I actually have a scale model of a phyton that I had 3D printed because I'm a nerd and figured out how to do that. But the cool thing about this, for what it's worth, is that it's actually the hardest part to print is actually this crossover region, right? And for what it's worth, that's actually what provides the most stability to the structure, right? Because that's actually what is non-natural about the structure of these crossover regions. It's also that, very similar to this model, it's very, very rigid, right? So, but unlike this model, it actually has curvature. So in fact, if you laid it across, it'd be 20 nanometers, but actually has some curvature to it. It's actually about 18 nanometers. And it's doing that enables us to tune. We can actually choose the components, but we can also change the geometry of the way that these are fretting with one another, right? And so we are relying upon fret, but as I'll show you in many different ways, we are not tandems, right? Because tandems change their fluorescence every time you put them onto an antibody. This is always fixed, because think about it. I have them literally physically fixed on this. I put them on an antibody. I guess I have to come up with an antibody thing. For now, I'll use this cowbell. But when we put it onto an antibody, that fret is fixed, right? So there you go. That's my antibody for now. But this also enables us the ability to think about, I've got 4 different independent arms of the structure. It also enables me to tune brightness, right? And like we've also used these to develop spectral signatures, although that's just something that where, we just know that the field isn't ready for that yet. So anyway, that's my new element for Catherine for today. But the way we've thought about this is, how can you think about this in terms of pixels, right? What if each detector and each laser line was actually a pixel on a graph, right? And the way that we can think about that is hitting each of these very uniquely, both be narrowly emitted and narrowly excited, right? And this is actually just showing our first 6 NovaFluors. And I'll use those as an example because I think they just provide like some nice handholds for, okay, well, how do we think around developing labels? And so the first part of this was just the thesis, which is, okay, well, PE dazzle is broadly excited by the 488, 532, and 561 lines. What if we just separated up that excitation, right? And the fun thing about this is, like, this is something that all of us have thought about, and we just haven't drawn it out, right? And that I think is what is hopefully interesting about this. And at least it wasn't for me. It was like, oh yeah, that's what I've been looking for. Because what if we just excited the yellow off the yellow and the red off the red? And what if we design fluorophores for the entire spectrum, right? Not just do an organic chemistry project to say, okay, well, we've got that dye, and well, it bleeds in a violet, but we'll just accept it. And that's the way we've thought about this. In fact, for what it's worth, we'll throw out labels that have too much spread or are cross-excited above a certain threshold, because we are designing for the whole spectrum, right? And so as I'll describe in a moment, we've got labels for 3 laser lines. Really, there's only 2 that are remaining, and we're very actively developing for violet and UV. And so again, focusing in on these 6 labels as an example, though, we've got, and these are named based on their excitation and their emission, something like a FITC replacement here or PE here, but they're also very narrowly emitting, right? To the point where even off the red line, we've done 2 that are even 10 nanometers different than each other, right? And so when you have that, right, the bar that I said earlier was like, okay, well, we've been very obsessed with spread. So what does that look like objectively, right? And the answer is actually stealing from, adapting from Laura's presentation, because like this article is like one of my favorites, and she's at U Chicago. So I just know that we send so many people to go look at that, because it's like, that's the bar, right? And so you guys have said, it was your blog post that said that's the bar. And so we're like, okay, that's the bar we got to meet. And, the answer is like, okay, sure. That's the bar that we'll meet, right? Which is that if you can limit cross excitation and you can have this kind of clean fluorescence, you really should be able to line up the standard deviations of these populations, right? I jokingly said one time, we can make quad gates great again. That turns out to not be a thing that people say, right? And so we've also looked at this objectively, right? And said, okay, for instance, now can we look at this across a set of labels, right? Can we look at this in terms of the quantitative notion of spread and look at how it affects other types of labels, right? And so no trumpet effect, which I can say here. Sometimes I have to explain it, but now I feel like I'm in home territory because you guys set the bar. So how do these labels compare to other things that are out there, right? And so for us, one of the things we do is we do a lot of benchmarking. So I'll show you some of the benchmarking that we've done. This is some benchmarking we did in collaboration with NIH. And then we've done a large series of benchmarking, particularly as we put out new labels around how do these compare to what else is out there commercially. We've done that in 2 different ways. One is like, okay, what do they look like in single stain controls? And the other one, of course, that's important for us is, well, how do they look in panels? So I'll show you some of I'll show you both of those pieces. In this case, we're taking the apples to apples. Okay, how does Nova Blue 610 compare to Brilliant Blue 630? It's not as bright, but put a pin in that because I can actually change the brightness of this label. But also note it's incredibly quiet in the violet, right? As well as the UV, right? And so, arguably this Brilliant Blue dye is a better violet dye than is blue dye, right? And of course, what we want to do is protect the violet space for multiplexing, right? Because honestly, there's quite a bit of spectrum there. And, as we look forward, again, transparently, we see a lot of area in the violet where if you could do very, very good fluorophores there, you could do a lot more in the violet than we even are doing currently, right? I would argue that the same is true off the red. I mean, here you've got a fac-symphony instrument that's only got 3 detectors off of the red. That seems like a shame, honestly, right? I mean, we've already developed 4 labels off of the red, and we've gone from APC to APC side 5.5 replacements, and we can certainly build out into the farther red. Again, a benchmarking here for NovaL 610 versus Alexis 694, PECF 594, and then also ECD, right? We are brighter than Alexis 694, nearly as bright as this PECF 594, and brighter than this ECD dye. But again, when we look in the violet and the UV, we've got this characteristic of being very, very quiet, and if you will, protecting that space. And then, as well, not as much emission in the blue, which is on purpose, right? We want to also use these in combination with a stacked approach in the blue. So off the Fact Symphony and other instruments, this is actually the type of sort of panels that we discuss with customers now, right? Which we say, like, okay, remove the PE or a PE conjugate, and then let's go in there and we can upgrade the panel, right? Because we can actually go in there and hit those detectors, right? And it's some of the work we've done, even on the high end when we do 40 colors or other things that help us frame those conversations, right? Because we can say, look, you can do this and you can essentially take spread out of your panel, right? And you can quite literally take spread away. And so, when we stacked up the NovaYellow 610 versus 30 other dyes, we saw that its aggregate spillover spreading error sum was the lowest among 30 dyes. And then on an apples to apples basis, Nova Blue dye, as you'd expect, versus Brilliant Blue was really good, a good performer, right? I'm definitely like a don't take my word for it kind of guy. This is some data that's from NIAD. We've also had, Oliver Burton at the Abraham Institute, show the same thing off of the Aurora, right? Which is that, our fluors just have a much more restricted emission, right? And for him, his piece wasn't, maxing out spectral to get as many colors as humanly possible, but more, hey, can I have clean fluorophores on here? Because he's doing a CRISPR-based flow screen. Can I have very, very clean fluors so that I can get high fidelity in my end result, right? Which actually turns out to be part of the other work that we're doing with another group at NIAD around chemokine receptors, actually, because they want to have incredible faith that any of the chemokine receptors that they have in a part of the spectrum aren't the biology they're seeing isn't because of spillover, but it's actually because you're getting these really good results, or you're getting these really clean fluors that are giving you good biology off those lymphocytes. So to kind of roll that forward, right, had tons of questions, right, and we've built on top of this now. But one was, how do these work with brilliant stain buffers, right? Can they be leveraged in larger master mixes? Can you also just plug and play these labels, right? So if you have low spreading labels, shouldn't you just be able to put them on antigens and put them in your panel, right? And we've got customers now that are doing that, right? Which is, you design a panel, of course, and there's 3 more publications that come out and maybe 3 or 4 more markers that you want to put on them. In the current environment, good luck, right? Like you just cannot simply add them on, right? And so we wanted to do that and say, okay, well, is that possible now, right? And then the other thing we want to do, kind of getting this background, this notion of spread, is when you push this to its absolute limit, what's the spread, right? Because if you think about it, this should inform not just spectral, but all other conventional panels as well. Because if they're low spread in this environment, then it's going to be the same as you have less detectors or less resolution. So the hand that we're dealt in many ways is this 34 color backbone on which we built this, right? And so what we did is actually compare, okay, how much spread are we adding to that 34 color backbone? And so Seth and our team added each of these first 6 colors one at a time onto the 40 color backbone, and then said, okay, well, what's the spread contribution, right? What does that mean? And what are the implications of that? And I think that's actually where we're taking a lot of this now is, we sort of had the lens of like fluors. And now I think we're taking a step back to say, okay, what's the implication of that, right? And so, the first thing we saw in Nova Blue 530, we're trying to cram it in there into B1 and B2 with BB515 and FITC. Friends don't let friends use BB515 and FITC together. Honestly, just the similarity and indices are just too much. What we're doing actually in our own panel, even though FITC was a really big contributor to spread, was actually we're dropping out BB515 and now using Nova Blue 530 and FITC together because there's less complexity there. That turns out to perform really well. Nova Blue 530 gets in the B1 channel and it's incredibly clean there. But I think the other thing too is to note is like is honestly what you're not seeing here, right? Which is that one, you don't see any off-target spread, and then for Nova Blue 610 and 660, you just have little to no change in the spillover, right? And so in many ways you get a free upgrade. And so in fact, we're talking to customers now who are they go back to this notion of panel design, being able to add these things in. Now you can quite literally do that, right, and not have an impact on spread. And to me, that gets really exciting because the number of times where I was designing a panel and then I ran it and then you wanted to ask even 2 other questions, but couldn't do it, it's incredibly limiting, right? And I think this kind of paves the way for us in terms of, okay, now the implication is you've got options to do that. And not only off the blue laser, which, sometimes it doesn't have some of the best brightness, but also off of the yellow, right? And so what we see here is we do get incremental increases in spread when we put these labels in, but it's in the labels that they're intended to replace in a conventional flow cytometer, right? In fact, they're all still totally analyzable, right? It's the stuff that we see off the back end of this, these spread increases aren't the things that you see when you look at like PE Sci5 or look at BB510, right? They still can be all used together, right? Which is the beauty of this. And we've actually built out more now in the yellow, actually, after having seen this, and then also moved brighter in the yellow, particularly off like a 700 and a 720, because sometimes you still want to have access to low antigen density markers. And the yellow laser, honestly, in our hands and for all of us, right, has honestly been a good laser for doing that, right? And so this again showed us the way, because it was also, there's no spread added anywhere else, right? Even in a completely packed out panel, right? So we did the phenotyping for this. We shared both the raw data as well as the deconvoluted data as well as the analysis on this. By the way, we will be doing that again, as crazy as that seems to people. So the second we analyze the data, we'll be posting up all of our data again. And I think the part that we're trying to drive to here is, like, I hate to say this, it's kind of like we're in this together when it comes to panel design. It's like all of these things help us look at different perspectives on panel design, right? And so for us, we learned a lot in iteratively working through these panels and essentially thinking about, okay, what's the hit list we should do? What should we replace? What will we never do again, right? Like in the violet, for instance. And so anyway, that was part of the reason for sharing that. The other reason, though, is also that, we leverage the NovaFluors and their clean fluorescence also to look at variable and low antigen density markers here, right? For instance, some of the chemokine receptors, right, where you're getting a lot of biological variability, which is interesting, right? And they might not fit into nice, neat little bins, and that's fine, right? And I just quite like that notion. So we've also just essentially thrown this against the wall and said, here you go, right? And it's exactly what we're doing now for the 45 color data. To that point, like, where are we on that? And so I mentioned earlier, we essentially have been setting a hit list. And so what we're doing now is, FITC, it turns out that FITC in combination with NovaBlue 530 is actually more tenable than a BB 515. And so what we've done is drop 510 out of a panel. And what we're doing is we can drop these, if you will, badly spreading dyes out and then come back in. And I think the fun thing about this, I had said earlier, removing spread, we've actually gone in and categorically defined that, right? Because now you can go back in and look at what would a hypothetical 37 color panel look like if I were able to remove these floors, right? And this is the answer. You can actually take out a huge amount of spread out of the panel, right? And we think that this is actually a really nice way of thinking around, okay, well, what would you do to do that type of iterative panel design? So we've done this for these 3 floors. I'll sort of spill the beans a little bit. The next one was PE Sci-5, which we also dropped out and replaced, which I think you'd expect, right? Because once you do this and you drop the spread out, where do you end up? You end up with a new hit list, right? Because then you can look at it and you say, okay, my next worst performer is PE Sci-5, and you remove it, right? And that's actually where we are right now. And when you can drop those out, you can come back in and then replace them with floors. And you can do that even off of nearly adjacent detectors. And that's exactly what we've run. And it ended up leading to some other ways, which the other things, which we'll mention in a moment, which is, well, crikey, like, how do you manufacture like that many antibodies across having that many colors, right? And so I'll discuss how we did that in a minute too, because I think it's kind of the how that's just as fun as the fact that you can run N colors. That's not actually as important as, like, okay, well, what are the things that you learned as a result of that, right? And how do you think about it, or panel design where you can take spread away from the panel to get some better biology off the back end of it? So the other part of this was, like, honestly, this feels like a little bit like therapy, but what is the stability that we've seen with tandem dyes, right? And how can we go after that? Because, when I show people new colors, they're like, hey, that's great. But here in the real world, like, these things need to work really well. And by the way, one of the biggest pains of any of those other experiments, 40, 45, is the fact that you have to use the BUVs like 2 hours before in creating your master mixes. Holy smoke. I mean, otherwise we could make a master mix that has that, even if it's a high volume, and have it ready. Anyway, I digress. I guess that'll be my next book. When I write my first book, it'll be Zen and the Art of Master Mixes. I'm trying out these jokes. This is fresh content. So obviously it's more funny to laugh at me when I say that than with me. That's okay. It's all right. I'm used to it. I'm just trying to keep people entertained. We spend our whole lives on Zoom. So what's up with tandem dyes? Okay, I mean, this has been known, but they exhibit instability in solution, leading to false positives, right? This is an intracellular, some data from Holden Maker and Joe Trotter. And you can see you get these false positives in, for instance, looking at interferon gamma, only when you have the CD8 APC Cy7 antibody in there, right? And in fact, if you remove that antibody, these false positives go away. And it's because in solution, you're getting the degradation of APC Cy7 into APC, right? You see the same thing for PE Cy7. By the way, I thought this was amazing. I can't believe I missed this, but there's a 2009 paper that actually looked at degradation and the fact that it was cell type specific. So you can actually bind these onto cells and then look over time, and you get different amounts of degradation depending on the cell phenotype, which is scary as it is interesting, right? So particularly if you look at something like monocytes, you actually even after 30 minutes are getting quite a bit of degradation in both APC-Cy7 and APC-H7. I thought it was really intriguing, and I thought, wow, that's also scary. The other one that we first focused in on was also the tandem dyes breakdown in fixative solution. And don't worry, I'm teeing this up, so I'll show you how life can be different. But this is APC-Cy7 breaking down into APC just after 72 hours in fixative, right? In the dark, light protected, but a huge amount. And then also some data from customers just looking at, this was actually over a 6-month period from Trisha at the Broad, looking at even lot to lot and then even vial to vial variability with respect to this marker on APC-Cy7, right? And so honestly, I think that the sum of all that is kind of crazy, in addition to the fact that when you use any of these tandem dyes, you also have to compensate on exactly that tandem dye, right? Not even a one that you purchased a month later. So we've been somewhat obsessed now on this front. So that we've done a number of different tests, and I'll show you these, but how stable are just the fluorophores, right? Just the phyton labels. So we just left them at 2 weeks at room temperature and then came back in and looked at them spectrally. There is no difference in their performance. And I'll show you this extends to the antibodies themselves, which you can leave out on a bench. I don't recommend that you do, but you can. So the other thing is that we want to look at is fixative stability, right? So this is breakdown after 72 hours. What we did is actually test fixative stability by leaving the stained cells in fixative solution for 2 weeks, right? Not fixing and then coming back with PBS, just literally leaving them in fixative for 2 weeks, which would just destroy a tandem. What we see there is that there's actually no difference. So this is just fresh. We can stain T cells, so that's good. We can do flow. But what we did here is compare fixed and fresh, those that have been fixed for 2 weeks with the label, and there's actually no difference in the signal. We haven't run this on an Aurora yet, but we did look at this on the Attune, because the question we kept having was, well, how does it look spectrally, right? First pass on the Attune, the answer is it looks spectrally stable as well, right? So you'd be able to fix and come back. So yes, we need to run this on an Aurora for sure, or at some point we might get access to an ID7000, which I think it's just fun from like a fluorophore perspective, having access to an instrument like that, because then you could look at the entire profile and say, okay, how spectrally stable are these under different conditions? But our first indication is that they're incredibly spectrally stable in fixative. The other thing we've done is also look at room temperature stability in many different ways. And so we've looked at this after 2 weeks, and we quite literally just left antibodies inside of a lab drawer, light protected, and then looked at this through several different lenses. The first one is, okay, what do they look like after 2 weeks just on signal? And the answer is, well, there's no difference, right? And so we're doing longer term testing now, but we thought it was important when we showed this to say, okay, the signals are the same. What about medium fluorescence intensity? What about separation indices? So we also looked at MFIs. There's no change in these MFIs, right, across this entire time course. And that also applies, so you could say, okay, that's great, but what happens if you're getting an increase in background, right? And so we also looked at separation indices to say, okay, well, we should also account for the 84th percentile of the negative, just in case there's some breakdown that's leading to increased background. And what we see is that there is also no difference in the separation indices, right? And that's always the bar that we set, which is that, it shouldn't just be, oh, it's just as bright, because if the background moves up, who cares, right? So similarly, we've done, I would say we'd have a similar paradigm when it comes to consistency. So we've been ordering tons of antibodies, as you've seen. And one of the things we've seen is high variability, lot to lot. And a lot of that, antibody manufacturing is pretty simple, honestly. So a lot of that's, in our hands is down to the fluorophore variability, right? The ones that we get from other vendors. And so we said, look, that's unacceptable. It should not be put onto the customer to say, oh, there's a lot to lot issue here. So what we do is we actually share our lot to lot data from manufacturing. So these are our 2 different manufacturing lots of our fluorophores. And the reason you're not seeing any differences is because there are none, right? So our spec is to keep fluorophores within 5% variability. In other words, the variability of the instrument. So if it's any more than 5%, it gets thrown out, because that's just not acceptable, right? And the other part, if you think about it from the point of view of the value of these being in their spectral clarity and in their performance, that performance better be the same, right? Like from here now and 5 years from now. And so the addition to this, though, is that now that we've moved into conjugated antibodies and have the ability to print these colors, which are obviously, as I've shown you, very stable, very consistent, but can now print these on antibodies. What does that look like, right? And so what we did is conjugate both these to CD4, the same lot of CD4, and then sent them off to NIAID and said, look, run these, run them across a titration and tell us if there's any difference in the separation indices. Again, using that lens of also looking at the background. And there was no statistically significant differences for any of our Nova Yellow CD4s or our Nova Blue CD4s. So we think that's the bar that should be set. So we've actually, I guess maybe somewhat tongue in cheek, but also kind of like, wait, why didn't we do this before? We came up with a checklist of things to ask your vendor. Like, have you looked for room temperature stability? What's the stability of this in fixative? Can you show me your lot to lot data for your fluorophores? Can you show me your lot to lot data for your antibodies? Because I mean, honestly, like personally, like as we run these experiments, that shouldn't be on us. And so that's the lens we're applying. I'll get off my high horse and show you some cellular data. So here we're just getting on lymphocytes. This is brand new data, and we're repeating this now across particularly because of the result I'll show you in a moment for what we did inside the nucleus. But getting on lymphocytes here, looking at fluorescence -1. This is just a positive control to show you that we can in fact stain interferon gamma. I think the exciting thing though for us now is, even though we're not up at saturation, is we conjugated Nova Yellow 660 to interferon gamma, and we are getting really good staining with low background. Right, and this was the question because of what I showed earlier with the size of these things. They're about 150 kilodaltons, so they're about the same size as an IgG molecule. So while I could like hand wave and say, oh well, they're smaller than PE, it'll get in. A lot of questions, right? I mean, it's a DNA structure, so what does the background look like, right? And so what we do here is actually just we do a higher dose of blocking after we do a permeabilization. But we've tested this in saponin-based fixation, and then the next one is actually a methanol-based fixation. And so this was the second part of this was, okay, net of that, can you also get inside of the nucleus with the structure? Again, gating on lymphocytes, looking at FMO, so low background on both of these. And this is where it got really interesting. So these are some experiments that we're repeating now and then scaling across other nuclear factors. But FOXP3, this is a titration of that antibody. You can see that the maximum fluorescence we get is about a tick over 10 to the 4. Things get interesting now when you look at FOXP3 Nova Yellow 610, because in fact, what you're seeing is actually there's this brighter species, right? So you're actually able to get, it looks like you're able to separate the FOXP3 high and FOXP3 low Tregs, right? And a lot of this we think is actually down to the physics of the platform. It doesn't have this 240 kilodalton structure hanging off of it. And in fact, in many ways, if you think about the two things in solution, it's not like there's chirality, but like there's actually a good amount of flexibility between the antibody and the phyton. So the way that they're able to get in the nucleus and access species might actually be a bit better. So we're testing that now across a larger set of samples. And then we also want to look at other transcription factors, right? To say, okay, can you replicate that kind of performance? Because on its at baseline, Nova Yellow 610 is not brighter than PE, right? Essentially nothing is, right? So I think we're really interested in that. And then if that's true, what we want to do then is, of course, multiplex inside the cell, right? So you can think about doing phosphostats or doing multiple different nuclear factors, right? In multiplex, leveraging that clean fluorescence, right? Sort of like the joke I always have is like, it's kind of like the promise of cytometry, but you can actually do real work on it, right? As opposed to blowing it through a 10,000 Kelvin flame. So the final part of this is controllable brightness, right? Which is this new to world capability. We had to come up with a way of naming all these things first, which is actually a lot. It seems easy now because I showed the light bulb. What I should do is really say like, well, how would you do it? Because like it was like, how do we think around naming these? There's no naming conventions for brightness when you can tune the brightness of something, right? Because it's just like, here's PE, deal with it, right? Or here's APC, and there's your brightness chart. Good luck. And for us, what we ended up coming up with was, let's name these based on the separation indices on CD4 off in Aurora, right? Like, and then let's just say that that's going to be the wattage of each one of these. And of course, separation indices are going to change, but it gives people a good idea of, okay, well, what are you talking about with respect to these brightness versions? To me, what makes this a lot less abstract, of course, is looking at the data. And you can see, we actually have honestly a pretty good ability of even separating these, even if they were on different markers in a channel, which is something we're running to ground now. But you've got a factor of brightness here, right? In this case, 30S, 70S, and then 60S up to 120S, and it's more than 3 times as bright over here off the Nova Yellow 660. So I think a couple of interesting things to point out here. One is you could look at lower antigen density markers and go brighter, but then the inverse is also true. You have very, very high antigen density markers. And we've actually had to leverage this just recently where we were doing a conjugation on CD44, and it was far too bright. And so we actually we said, okay, what's the lowest brightness that we could have across those fluorophores, and then say, okay, drop it into there, right? And then essentially bring that down to not spread elsewhere into our panel, which was honestly a lot of fun to have the flexibility to be able to do that. The other thing too, as I mentioned, is right now what we're looking at is the similarity indices of these different enough that you could actually use them as independent markers. because we've had a lot of questions around like, could you use these as barcodes? Are these separable? So I hope to know more about that soon, because the point is what our goal is to build out actually a menu of these digitally brightness floors in channels where it matters, right? So you could actually end up choosing, okay, well, I want a brighter version here or a less bright version here, right? Independent of the color, right? Which I think is going to take us hopefully to a new place in panel design where we could say not just, oh gosh, my panel didn't work and now I need to go and re-engineer it, but instead I just need to titrate essentially the brightness of these, and I can choose that and actually look at this. So that was part of this launch that we did a couple of months ago, which was where we've now done 19 labels in 6 months. So that was 17 unique colors. And what we've done, I've shown these first 6 colors, and because I think they just provide a good example. We've really kind of spanned FITC, if you will, right? We're sort of built out a full menu in the blue because now you can actually use your blue laser, right? Because if you have very clean fluorescence in the yellow, then you can unlock that laser. Built out of really kind of a suite, if you will, around yellow, particularly some very bright labels to replace PEP conjugates because there's still, still low antigen density markers out there. And then moved into the red between APC and APC Sci-Fi. The latter one being one that was really honestly just hard to get our hands on, and because it's not commercially available sometimes. And so we said, okay, let's just go and make a replacement for it, right? And you can see too, I think the other point is, we're hitting gaps here of 10 and 20 nanometers, right? And still, and we're that's on purpose, right? And it's so that we can go in and really think around, okay, like what kind of pressure can we apply to the hardware manufacturers so that we can get, if you have clean fluorescence, you should have detectors every 10 to 15 nanometers and be able to use them all together, right? So the other part of this, of course, was benchmarking. So we've benchmarked all of these against current floors, right? And so the way that we do that is also by looking at both separation index, which, again, we're kind of think a lot around background too, as well as spread, right? And of course, there's a relation here, right? And obviously the spread is going to increase with signal intensity here, right? There's going to be this linear relationship. But I think it's important, right? Because it also just enables us to think around a framework of also the way the different lasers are behaving, right? Obviously, you've got blue kind of hanging around here, at lower signal intensity. We created this interactive resource where you can actually take a look at our floors stacked up versus the other floors that we benchmark against, right? And so the goal now also is to take this, and by the way, you can look at it by laser line as well. The goal now is to take this and create profile pages to show all the benchmarking that we do for every single one of our labels versus all others. Because it is still a good amount to navigate. So we've done, what have we done net of all that? So we've done these conjugation kits, which are these 1 by 100 microgram kits across all of the colors. We've done CD4 kits as well, which are really nice ways of characterizing the labels across a whole set of instruments. And that, again, thinking around this notion of spread and how we can think around panel design. But those have been great. I think it's a great way for people to put their hands on it. I think the new update there, because one of the things was like, okay, well, we're going from being a label company to being able to provide conjugated antibodies, was okay, if we're going to go and do that, how do you do that in a bit of a different way, right? And so that was the question we asked ourselves. And so, one of the things is, if you go to a catalog right now, you'll see something that says something like this: typical FTP ratio 3 to 7 to 1, right? So which, fluorophore to protein, in other words, fluorophore to antibody ratio. And that's a pretty big band, right? And if you think about that, it's not just PE. Like PE is big, so it's easy. You put one PE on one antibody and it occludes the other PEs from binding. It's not the case with some antibodies, but that's a pretty big variability to have on the number of fluorophores you have on a protein. And the way I think about this is that's variability that you have before you ever even get on the cytometer, because there's a Poisson distribution of these fluorophores on the antibody, right? It's also that this affects cost, because to make these things, you've got to add excess fluorophore to the system to bind them onto that. And for what it's worth, in customs programs, this also might lead to free dye coming out the back end because you do have that excess, right? And so there was a lot in that, and honestly, this is something I had no idea about until about less than a year ago. And I thought, wait, what? And so what we did is said, okay, if we're going to really go in and change that, and we know that we've got a fixed number of dyes on the phytons themselves, can we come up with a way of doing one-to-one conjugation where you have only one phyton on one antibody and you don't have that Poisson distribution anymore, or at least can limit it down pretty significantly, right? And so that's actually what we've moved to. So we do have a one-to-one conjugation program now. What we've done with that is actually we've got our certain set of menu now that we've got, right? We've got these 12 specificities across mouse and human. But I think the more kind of fun update here is actually our ability to leverage that for any of our in-stock antibodies, which we can then print out on new colors, but then we can also take in any antibody from anybody, do a one-to-one conjugation on that on any of our in-stock colors, and do it, this should say now on our customs program, 3 weeks or less. We're actually able to print those out and verify that it's a one phyton on one antibody interaction, right? And so we've done that now, and we've just scaled that up to the point where we can meet our needs, right? And we've done a number of custom order for government institutions and biopharma. And I think it's pretty exciting because we get to the point where it's no free dye, a one-to-one, one phyton on one antibody, and it's on your antibody, and it's back to you in 3 weeks or less, right? And so the goal is actually to beat that. 3 weeks is a max. And so this is pretty exciting. So we're going to be showing a larger data packet of this, actually just in 2 days' time, just showing like, okay, how are we our own, like how do we eat our own dog food, right? Like how do you, if you go out and you request 8 specificities, how do you then go and validate that? For what it's worth, what's fun about having these is when we have all these polynucleotide modified antibodies, what we can do is once we've got that essentially in the hopper, it can be put on any color. Right? Because once it's polynucleotide modified, we come in with the strand that reacts to that has the phyton on, right? And that turns out to be really efficient. You can purify that out the back end, and you end up with a pretty high yield amount of antibody, right? No excess dye, right? And all one-to-one. So I think it's exciting too because where we're moving to is to actually really be able to make flow quantitative. Because if we've got one phyton on one antibody, and you run a standard curve, you can get to the number of molecules, right? So that's some work that we're just starting in on right now that we have control on this and can do this at scale. It's one of the fun things we really want to do with customers, right? Which is like, let's go in and run that, right? So what are we up to now? Very actively developing labels in the UV and the violet. This is also an area where we take a lot of, as much feedback as you're willing to give on the super brights or the BVs or the BUVs. Super helpful for us, right? Because again, when we land in a laser line, it's not like, oh, here's one label, right? We land with the intent of building out a whole suite of labels, right? And I think where we're trying to understand there is what brightness, what wavelengths, what practical considerations too, right? Beyond just like the 2-hour master mixing, but like, aggregates are another issue for these dyes, and we certainly have never seen anything like that, right? But all that's incredibly useful for us. So that's we are engaging on Purple Rain right now, and or hopefully have a lot more to say about that early next year, just in terms of like what the number of labels are there. But as much feedback as you're willing to give, we take in. It's just super important. So yeah, we're Photonics. We've done 19 labels actually in 17 colors in the first half of this year. Our catalog is also up, but I would say that our website always is like way behind it. Like it's like when you're running a race and you can't see the person behind you anymore. Like we're running ahead with printing and the ability to do that. And our website is a mile back from us. So I mean, maybe it shows where our focus is, which maybe it's in the right space. But yeah, hopefully some fun points in here and hopefully interesting.
Thanks so much. That was great.
Thanks, David.
Thanks. Since there's really not many of us in this at all, I'm going to just open it up, and if anyone has any questions.
Hi, Laura.
Hi.
Actually, so I loved your the talk you gave at Cyto, and one of the points you made, and I was wondering if you can revisit a bit, is the idea that the problem you identified is the fact that we have a set of antibodies for every single technologies we're gonna use, and it seems like you were hinting at a way that Phytonex would be able to transit from one technology to the next. And do you want to talk a bit about that, or?
Yeah,
that's quite in the.
Yeah, it's something that we're quite literally filing and working on now, but that would be the ability to have the one reagent to rule them all, right? And to, because if you think about it, I've got a DNA platform where I have fluorophores, right? And inherently that means I've also have the ability to put unique sequences on there. And then also, and you can always hear, there's always a notion of quantitation, right? Because that's another issue that you deal with. Very similar to fluorescence. I think people forget this. They're like, oh, I sequenced it, it's fine. Not really, right? Like, how do you prevent from dropouts there? How do you tune that relative to the dynamic range of sequencing, right? And then what else are you trying to do in an assay that might essentially in many ways drown out the ability for you to detect a certain protein? So I think the answer is Yes, very much so. And the beautiful thing about it is as we work towards, for instance, a larger dynamic range in fluorescence, the same applies in genomics, right? And so I think that's very active. And then I'd say another active area for us too is, okay, what can we do in imaging? And by the very same token, could you do that? Could you do imaging in addition to genomics and have one platform to do that? And so, I think it's, I don't say it's like slower than everything's slower than I'd like, but it's going, unfortunately we have to make new colors, right? Like, and we have to make antibodies and but the answer is yes. I think that's something that is of extreme interest to me. And it's also that, frankly, we've done a lot of work in characterizing a lot of the sequence tagged antibodies that are commercially available and have not been impressed, which would be the understatement of a lifetime, right? We've got so we've seen that some antibodies get killed based on the conjugation of oligos to that antibody, right? Because I think where we spent, as you can see, where we spent a lot of time is oligo conjugation antibodies, right? And we've gone through a lot of different kits on that, a lot of different technologies, and we realized, I think our hope was, we'll just be able to use something that's just off the shelf to be able to do this. And what we found instead is that's not the case, right? We have to go out and develop a chemistry for that we could control, do quantitatively, and then come along with the phyton to ensure that it was one-to-one. Because there are tons of antibodies. I mean, there's commercially available antibodies that are out there that have been killed based on that conjugation, which I think is shocking. And so I think in uncovering that, I think we've seen a lot more of the underside that I didn't expect. So anyway, I'm really hoping that we can have more on that. But now it's just like, okay, how do you develop for that? And then how do you also show, for instance, you could do some of this biological normalization, right? I think particularly when you're thinking around multi-omic assays, I think it becomes really intriguing. Similarly, I think one of the other questions you could have is on both those technologies, how low can you go? Mm-hmm. Right. And the other part that I'm not showing here is just the amount of dynamic range you can have from this platform it's honestly insane. We're going to get down into the very few number of molecules very, very soon. And I think that's really exciting. And the question then just becomes how do you manifest that, right? How do you enable people to do a single molecule or 10 molecule type flow? And does that preclude you from doing anything else, right? Because there's always going to be some sort of trade-off there, I think.
Right.
So yeah, hopefully I answered your question. It's, it's moving along. I'm pretty stoked about the ability to do that sorting and then just be able to move right in.
I would like to ask a question about the stability of the phitons.
Please.
So, we have a lot of our users are not users of making these huge panels. I run a core facility. And so, but when there are people who don't frequently use the facility and then they have these tandem dyes and they poop out after they use them 2 or 3 times. And if we had some nice data that these would be, stable longer than the tandems, then that would be actually something that would be a selling point for people who aren't, the high-end users.
Yep, absolutely. So yeah, we've got data on essentially 3 months storage, and we're building out more of that. But they're rock solid. So yeah, I think we've got I've got a whole talk that is essentially it's an obsessive talk about consistency and stability. And I think what we'll do is we'll send that your way because it is literally a data packet on just how far you can push the platform. And hopefully that would be of use to your users because it's all of, that tandem dye slide I showed that shows all their problems. It's all the ways that's not, that we should contrast ourselves against. And even in that, even if they said, I'm not that interested, it still provides them a checklist that says, these are things you should be thinking about and asking of your vendor with respect to either tandem dyes or other dyes, which I think on its own is useful, right? It's because we've earned I think all of us have earned our scars on that.
Yeah. Very good. Well, thank you. That's helpful.
Absolutely. Thank you for your post on spread that I've read so many. I don't even want to tell you how many times. Maybe you could sign a copy of it. That's how many times we've read it. And I'm not just complimenting you. It's we literally refer to that all the time. And it's so bad that we refer to it as a trumpet effect in-house now, and then we have to go explain ourselves every time we say it. So now I can just say, well, I've actually met Laura. So
that was me. Pat was the one that asked the question. Pat's at Loyola.
I'm sorry. I didn't hear that.
I do have a question. It's possible I missed it because I also had to address a couple important emails while I was watching this. Did you talk about how there's this whole fiasco with compensation beads and when antibodies bind to compensation beads versus when antibodies bind to cells, there can be differences in the spectra?
There are, absolutely. We've seen that with our benchmarking as well. So we've done, so those things I showed you, we've done, every time we do a benchmarking, we do CD4 conjugates and we look at them on beads and cells, right? And there's no like magic in the fact that like every dye is different on cells and beads, right? I haven't seen anyone that is exactly the same, right? And so I think the lift there is that once you have essentially a single stain that's on cells, because of the consistency and because of the stability of these fluors, you should be set, right? Because there's very little difference now that you've run it on cells in between those spectra, right? So I think in thinking around attacking that problem, it's not necessarily that like you're going to be able to make a bead perform like a cell every time, right? But I think with respect to like once you have that signature, is that going to change? We haven't seen variability with respect to any of the spectral signature of the actual dyes changing, regardless of the antibody they're put onto.
Yeah, I was just wondering, because I think at the end you mentioned like if there were any issues with the brilliant violets or the super brights and whatnot. So I mean, really the problem is like, I try to tell people if they can bring single stain cells for their controls, but if they don't have a very good positive population, like if the marker just is really dim or it's a really rare population, then it can be challenging to bring single stain cells. So in that case, people tend to want to bring compensation beads as an alternative. But if there's a mismatch in the spectra for that particular antibody on compensation beads, then it becomes an issue with unmixing on the aurora. And so I found, I tell everyone to bring a full set of single stain, or like basically a double set of single stains for one of their experiments in order to figure out where the mismatch is and which controls need to be used. And people ask me like, is there a way that I can predict which fluorophores are going to be a problem on the compensation beads? And I found that it's just all over the place, but like depending on the compensation beads, there's certainly some compensation beads that are not good with the brilliant violets. Yeah. So I don't know if you guys have found similar issues like with different compensation beads, if there tends to be more issues with like the beads that don't do well with the brilliant violets, or if it's just kind of, is it like worse than the brilliant violets in terms of mismatch, or like?
So I think there's a couple different pieces in there. I mean, one is that we have never seen any difference in the fluorescence. Like you use CD4 as your single stain control and it's going to be the same. You know what I mean? Like I think from a let's compensate on cells perspective, you just don't have any of those issues on a like a specificity or conjugation basis. We just don't see those. We don't see those differences. So the first part is it just gets a lot easier because you could just use CD4, which we do. We use CD4 single stain controls for all the NovaFluors on cells, and that's what we use for deconvolution because it doesn't change. On the beads, I know we've looked at we've used the thermocomp beads, and then they've just released a essentially like a quieter in the red version of their beads, and a lot of that probably due to the fact that the gain is really turned up on that aurora in the red to separate two red markers in the kind of in like the 600 to 700 range, right? I think honestly over time, one of the things that again, it'll probably be one of these other inflammatory things. It's like we'll tell people to turn down the gain in the red. APDs are naturally more sensitive in the red, right? And so you could save yourself a lot of headaches in the red by turning that gain down as opposed to going with the default settings. I haven't done the rigorous bead comparison to see like specifically, are there issues in certain parts of the spectrum? But I think when we looked at it on thermo beads, there certainly isn't any more variability than other dyes. I mean, I think we do see differences between cells and beads, but I see that across every dye I've looked at. Yeah, so if you want, I know we've got a data set where we've looked beads versus cells across all the labels. What I'll try and do is dig that up and send it your way because I just haven't looked at it in a couple months, but I'll send it your way and then hopefully that adds to the insight here because I just can't remember. I don't remember the ribbon plots off the top of my head to be like, okay, yeah, there was a specific area that was really bad. And I just don't remember what the performance was.
Yeah, from what I've seen, it's literally like each individual antibody. So it's kind of this weird.
Wow. Yeah,
phenomenon.
on the Aurora we haven't seen that. And so remember too, because we're printing, we'll do like a print on a Nova 610, and then for all antibodies, and then we'll do it on another marker, right? And so I've never seen fluorophore differences in between our conjugations. It just doesn't happen. So yeah, I think for us, so yeah, sorry, the thing I was thinking was like color one cells, color one beads, but like between those colors, no, we don't see variability.
Yeah, I'm talking about the same antibody on beads versus the same antibody on cells. But it sounds like since there's so much consistency between all of the fluors, then maybe if people are having problems, they should just buy like a CD4 in the same color and stain cells.
Yeah, that's what we're doing now. I mean, given that we don't, I mean, given that there's no explanation for what's going on there.
Yeah, no one's figured out why it happens. Everyone just kind of agrees that it's a weird phenomenon.
Yeah, it's, I always go to Steve Perfetto and I'm like, what's going on here? And no explanation. I'm like, oh shit. Well, then I'm not gonna have any luck either in understanding that, right? And is there some sort of transfer from the autofluorescence to the beads, or like I don't know. But yeah, I'll pull that comparison data though, regardless, because I think I just haven't looked at it in a while and it's important.
Thanks.
So am I right in thinking that you guys are all like flow coordinators, essentially?
Yeah, me and Laura work in the same core facility, and Pat runs the Loyola Flow Lab.
Yeah, because
Pat,
I mean,
sorry.
The question really for me now is, where do we go from here, and how do we get your users to start using the NovaFluors? How do we start putting them into panels?
I was thinking about that, like, and actually this week we're recording a podcast, so to speak, with Kelly Lunson, and we asked her to mix all these different dyes that came out over the last year or so, because there's a bunch, like Sony launched theirs and Cytec, and it's a sea of new fluorophores that came out, and I think people have, like, when I started working, you had Alexa 48, Dialight 48, and then you had Pack Blue and E405, and like they were all the same molecule with different names, and I think people might have got used to different dyes shining in the same detectors were all the same in no difference. So now I think there's an effort to be made to just explain more about fluorophores and not just the excitation, emission, brightness, and explain like, what are they and what can you do with them, and because now there's actually something to be said about like the NovaFluors. So they're pretty exciting. So I think that's the.
Can you let me know about that? Because that'd be a really interesting topic. Kelly is actually very good at explaining the difference, the chemical differences between the dyes that we have available to us, and so it'd be really interesting for me personally to be able to do that. I mean, I learned all that I possibly could about Brilliant Violets being on tour with Kelly around Australia. I'd be really interested in that. But the question really then is, once she has managed to discern how different these are, how do we then get the message out to your users and then get them to start putting them into their panels?
Oh, well, then it's just generate data, show people what the difference is. So, like the impact of spreading, reducing spreading with using NovaFluors would definitely get people's attention, I'm pretty sure.
I would say for the Aurora users, in order to design an Aurora panel, and a lot of people do contact me in our core because I'm like the main Aurora. Everyone gets trained by me. All the Aurora users do, and then a lot of people will run their panels by me. I would say the thing that is most heavily relied upon is the spread matrix. So I go by what SciTech has given me for the spread matrix. And if you guys know where our website is and all of our spectral page on our website with all of the panel design tools, there's the spread matrix from SciTech, and it's 30 colors. And I think I can probably get the 35 color one from them now. But basically, if I don't have that spread matrix, then I don't know how to recommend things to people. So if you give me like a 25, 30, 35 color spread matrix with your fluorophores, then I can easily tell people to use your fluorophores and how to use them and what problems to look out for. But without that spread matrix, I feel a little bit lost as to where to place markers.
Definitely.
That's a fair point, Laura, and I'm pretty sure we could.
Got the 40, so, and then we'll just follow it on in like a week's time with a 45 as well. You know, because you're going to see different things, right? Because as you take out crap fluorophores, you're going to see something else, right? So hopefully that iteration makes sense. So.
Yeah, so like a big one, like a 40 color would be great, but if you want to go even further and kind of like if you go onto SciTech's website, they'll give you sort of like pre-planned panels. So they have like a 24 color panel, a 30 color panel, a 32 color panel. And they do them for like generic immunophenotyping, but it's also useful for people who want their own panel, but they want to use a certain number of markers. So like if they want to use 24 markers and people need to figure out what are the best 24 fluorophores to use for that panel. And if they just have a quick list of, okay, here's 24 colors, we know that these colors work really well together. We've minimized the spreading with these 24 colors. They're a good match for this size of panel, then that makes it really easy for people to do panel design. I mean, they can come up with that if you use SciTech's spectral analyzer and they have the complexity index. They do that, but if you guys already have it on hand, then that just makes it easy.
Yep.
Sure, we'll get that too, Laura. Okay, so yeah, I'll get that information to you. See if you can join us in a couple of days' time for the release of the 45 panel.
Yep.
And yeah, I'll be in touch. See if we can. I mean, you know, the other alternative really would be to start off with our CD4 kit. Laura, I don't know if you've had a play of that at all. Basically, you can you know, use it to have a look at CD4 across all of our current NovaFluors. I can send you information.
Dave and I talked about it, but I guess I hadn't come up with a goal of what I wanted to do with playing around with them. Yeah,
I mean, that in that way, you'd be able to just characterize the NovaFluor on CD4 across.
That's true. On
your instrument, that's it. And then you'll have a better idea of how to then recommend it to your users. The other alternative is just to start dropping them into a panel. So how about I give you both? I'll send you an email following up and we'll just see how we go from there.
Sounds good.
Yeah.
Cool.
Thanks very much for all your time, guys. I really appreciate it.
Thank you.
Yeah.
Bye-bye.
Bye.